I'm David, I'm the coordinator of the Maths Learning Centre. Now you know what I look like, I'm going to turn that off. I think my campaign over the last several years of showing people what I look like in these has worked quite well. People are more likely to recognise my face and not just my voice, which is usually extremely well known. So this is a revision seminar for Maths 1A. It's semester 2, 2017. Hello from the past to everyone watching, and hello to you. As usual, I've taken some requests, and I now have a dilemma of what to actually cover. I'm hoping that all of you will be happy with me doing anything in particular, knowing that all of the past revision seminars are on the website, and they are organised by topic. So if you're particularly interested in trig substitution, for example, and I don't get to cover it today, you could go onto the Maths Learning Centre website and find the thing on trig substitutions, and I think there's even a couple there, and see what I had to say about it last time. Okay, well I might start with funky determinant stuff. So, it's going to make me feel uncomfortable. Let me go it that way. So determinants and other matrix stuff that's sort of related. That's what I'm going to talk about. So, if I was going to talk about all the things that I thought about determinants, the first thing I would say is that determinants hail from a time before matrices. Back in the day, when people worked on systems of linear equations, before matrices were a thing that people had thought of, there were determinants. And people would calculate determinants from the coefficients of a system of linear equations. And they survive today as things that you can do to matrices, because matrices are related to linear equations. And Lewis Carroll, the author of Alice in Wonderland, his research area as a mathematician was determinants. Nice little tidbit there. I think it's kind of cool. Yeah, so they survive as sort of a thing that you can do to matrices that just happens to be connected to a few of the other bits of information about matrices that you have. A lot of people who are in tertiary maths education think that it's a waste of time teaching people about determinants because the quickest way to tell if a matrix is invertible is to attempt to find its inverse. But I still think they're pretty cool. So, and you have to learn them, so we've got to suck it up. So, all right. So determinants are a piece of information about a matrix. So what you do is you create this calculation based on the entries in the matrix, and it produces a number. So you've got your matrix, you find the determinant, and you get a number. That's the basic idea of what determinants do. And the calculation that we do is quite complex, and it gets more and more complicated the bigger the matrix gets. But what we'd really be interested in is that every time you find a new thing that you can do to an object, you want to know how that interacts with all the other things that you can do to that object. So when with numbers, you first learn multiplication, it was a kind of a useful thing to start learning about how multiplication interacts with addition, because that was a thing that you used to be able to do to numbers. And so we have various things that we can do to matrices. We can add them, we can multiply them, we can do row operations on them, and it would be kind of useful to know how determinants interact with those other things. And that's when we say funky determinant stuff, that's sort of what we're doing. We're saying, how does determinants interact with the other stuff we can do to and know about matrices? But I wouldn't be complete if I actually didn't say how to calculate it. So how to calculate a determinant? Well, if you've got a 1 by 1 matrix, then the determinant is whatever number it is. I know that seems stupid, but it's the truth. So the determinant of the 1 by 1 matrix with the number 5 in it is 5. No one needs to know that, but it's just, you know, I'm a mathematician. I like to cover all my cases. The determinant of a 2 by 2 matrix is made by doing this. I'm going to colour code. I apologise if you can't tell the difference between these colours. That number times that number minus that number times that number. That purple is surprisingly brown. 3 times 6 minus 1 times 0. So in this case, the determinant is 18. Yay. And once you get bigger than that, it gets harder. A lot of people, if they learn matrices at school, I didn't learn matrices at school, I only learned them at university. A lot of people who learn matrices at school learn a fancy trick for doing determinants of 3 by 3 matrices. I don't find it worth trying to remember that fancy trick because, you know, I have other methods. If you happen to know the trick for 3 by 3, more power to you, but I'm not going to tell you now. To find the determinant of any bigger matrix, you create it out of smaller determinants. So the determinant of a 3 by 3 matrix is made by doing smaller determinants, but made out of the bits of the matrix that's there. So I can choose any row or any column I like, and I can use the entries in that row or column and the matrices that are left by removing that row or column and construct the determinant from that. So I might, for example, pick, you know, I'm going to pick the middle column, for example. So let's see. My middle column's here. It has a 0 and a 5 and a 3. And when I remove the entry, this position that the 0 is in, I'm left with 5, 7, 6, minus 4. And when I move the entry that that 5 is in, I get the row and column that the 5 is in, I get 1, minus 1, 6, minus 4. And I remove the entry that the 3 is in, I get 1, minus 1, 5, and 7. And that's not the only thing I have to do. I also have to keep track of whether I'm going to put a plus or a minus next to these numbers here. So they're going to have to be added or subtracted. And I do that by starting in the top left corner of my original matrix and putting pluses and minuses. So let's see, plus, minus, plus, minus. Okay, so it's minus this, plus this, minus this. And then what I'm going to have to do is figure out all of those smaller determinants. So that one's 0, so that's kind of pleasant. 5 times minus 4 minus 6 minus 3 times 7 minus 5. And then whatever that works out to be is the answer. 10, so that's 2, 10, 12, I think it's minus 26, but don't quote me on it. Okay, and if I had a 4 by 4 matrix, then I would need to turn that into 3 by 3 matrices, and then each of those 3 by 3s I would need to turn into 2 by 2s. until I got there. So it just takes this long process. There is a way of doing it directly, which is sort of fun. And I just think I want to mention it. That what you can do is you can take all possible combinations. So if you pick one entry in each column in such a way that they cover all the rows, so I could pick this one and that one and that one, for example. That's one entry in each column that covers all the rows. If I do all possible and then multiply them together, I do all possible combinations of them, and I multiply them by plus or minus 1 depending on how many row swaps it takes to get the identity matrix into that position. That's the determinant as well. There you go. Some books define that as the determinant with this big sum sign. So there you go. But this method works perfectly well. And what most people do is they pick a column or a row that has the most zeros in it, so that they can do this trick I just did here and go, oh, well, I don't have to figure out that bit because it works out to be 0. So if you've got a row or a column that's mostly zeros, that's probably the row or column you need to pick. Cool. That thing with the pluses or minuses is a useful thing to know because it comes back when you do cofactors. So just as a little, what's the word for it? In a book they normally call it, or in a play they'd call it an aside, where the actor turns over the side of the stage and tells you something interesting that they're thinking at the time. That's what I'm going to do now. So in a matrix that has entries like this, just make sure that when you do your determinants, you keep track is that it's always, at each layer you start again. So if you make 3 by 3 matrices, you'll start again with your pluses and minuses. You don't maintain the pluses and minuses from the original matrix. As long as you start with a plus in this top left corner, you can do whatever you want, as long as every time you switch positions, you switch signs. So plus, minus, 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 plus, minus. Ta-da! That's that checkerboard. If I try and do it across this way, go plus, minus, plus, I always get this next one wrong. When I know it's plus, minus, and then I try to do the next row, and I always forget where I'm up to and put a plus there instead of a minus. So if I just track round in a spiral, usually is what I normally do, then it turns out fine. And usually you don't need to know it for the entire matrix. You just need it for one row or column. So I'll start with the plus, minus, and get to the row I want, and then go along that way. So, which is what I did up there. Just in case you want to know. I find it efficient. I think it's fun. Okay. Right. Beautiful. That's calculating determinants. And it seems like a pretty complicated thing to do. And it is. But essentially it's about doing all possible row swaps, really. And that gets me to the next thing. So how does this interact with the things we do to matrices? And this is pretty good advice. Anytime you get a new thing that you can do, you should always ask how it interacts with the other stuff you do. So if at any point in your life you learned complex numbers, then you'd go, oh, now I have the conjugate. How does conjugation interact with plus, minus, times, divide, all the other things I do? Oh, now I've got the modulus. How does that interact with plus, minus, times, divide, and conjugate? Now I've got this new thing I can do. How does that interact with all the other things we do? When you learn a new function like sine or cos, you say, well, how does sine or cos interact with plus and minus? When I put a plus inside, am I allowed to expand it out over that or not? The sorts of questions you should ask yourself so that you know what rules are appropriate to use. I should go back here. I'm using det because that's just what I felt like today, but a lot of people use just those, vertical bars, the determinant of the matrix 5. They use vertical bars like the modulus sign to do the determinant, which is confusing because when we do the absolute value of whole numbers, or for complex numbers, you always get a positive answer. But with matrices, you don't always get a positive answer. So that's a bit confusing. Okay, so here's the stuff, how it interacts with other stuff we do. The determinant of A times B is the same as the determinant of A times the determinant of B. That's a really useful one. If you multiply matrices, then you can multiply their determinants. And it also turns out that the determinant, if your matrix does have an inverse, then the determinant of A inverse is the determinant of A inverse. It's kind of cool. Oh, it works with all the powers, actually, while I'm at it. The determinant of, like, A cubed is the determinant of A cubed, for example, but it works with squares and any other powers. You don't have to worry about it working, and worry about what happens when you have half powers, like, because there's no such thing as a square root of a matrix, so you don't have to worry about half powers. Okay. How does it interact with plus? That'd be useful. Determinant of A plus B is, well, who knows? There's no real way of telling how determinant will affect matrix addition. No clue. There is one thing I could do, but that's in very special circumstances. So there's one special circumstance, which is probably not in your lectures, so I'm not going to write it down, but if the matrix A and the matrix B are identical except for one row, then you can add their determinants. So, yeah, which is a bit of magic, really. Okay, so that's how it interacts with plus and times. What else can we do to matrices? We can invert them, we can multiply them, we can add them, we can... Okay, so there's one interaction that's not really an expanding out sort of thing, but it's a useful thing to know. How is it related to other information about a matrix? So the information of does it have a determinant, how is that related to the matrix? So we have determinant of A equals 0 is the same as saying that A has an inverse. That's cool. What else can we do to matrices?
What was that thing where you multiply one row of the matrix by a number and then the determinant is also...
Cool, yes, we are going to do that. I'll hold that for a second, because I was just thinking something. What was it? Transpose. We can do the transpose of a matrix. I just wanted to cover that before I forgot about it, otherwise it wouldn't happen. Transpose is a thing you can do to matrices, and when you do the transpose, the determinant doesn't change. It's exactly the same as it was before. And I guess that makes sense, because the numbers would work out, like the determinant of a matrix is just based on the numbers, and if you flip, like for a 2 by 2, if you flip those two around, it would come out the same. Okay, cool. Not that this is the thing you can do to matrix, but I reckon if you rotate it at 90 degrees, not that that's a thing you talk about, the determinant wouldn't change either, but there's no name for that operation. Okay, right, and you were saying that you could do things to the rows and that might change the determinant. So there is a thing we can do to matrices which is row operations, and they can change the determinant too. Okay. So if you multiply one row of a matrix by a number, then the determinant gets multiplied by that number. How do I write that down? Well, how about if I write it like this? If A goes to B by, row 3 is 5 row 3, then the determinant of B is 5 times the determinant of A. Yeah. Do you know what? I'm just going to change, I'm going to keep that. I'm just going to move it down a bit because I wanted, just thinking in my pictures, if A goes to B like this, then the determinant of A to get to the determinant of B, you times by 5. That's what's going on there. So if A transforms to B by doing 5 times any one row, then the determinant will be 5 times as well. But this other version is a useful version as well. And I'm going to write it down with some matrices like this. So the determinant of that, okay, so watch very closely. This is how I normally write my working. So that matrix there has the middle row, 5 goes into every one of those. So it could have been produced by doing 5 times a row of an old matrix, which is lots of backwards and forwards thinking, but I just think about, I can factorize a 5 out of that row, and then it'll come out of the determinant as well. Like that. So that's how I normally think about it when I do fancy stuff with determinants. I don't think about the row operations. I think about saying, well, I can pull a 5 out of that row and it'll come out of the determinant. And if I look closely, there's a 2 in this row as well, so I could pull that out too. So just so it's easier to see what happened there, that was me focusing on this row, which I pulled the 5 out of, and then I focused on this row, which I pulled the 2 out of. Not that anyone cares at the moment, because it's not making my job any easier. But I can do one more if I was really paying attention. You can do it with columns just as much as you can do it with rows. So I can look at this column, that first column, I can divide that one, pull the 3 out, if I so desired. So I could do that, happily as long as I like. And the reason you might want to do that is that you might feel a bit more comfortable working with multiplication when there's 1s instead of 3s, because your multiplication will be a little easier to do. Okay, so that's row operation number 1. The second kind of row operation would be if you swap some rows. So if A goes to B by doing a row swap, so row 1 and row 2 become row 2 and row 1, like that. So that's a row swap. Then what will happen to the determinant is it will be times by minus 1. That'll go just as well for columns. I should probably say that. Works for columns too. Now that one's probably less relevant than most of the things you care about, because when you do determinants by hand, you can expand them out along any row or column you want, so why would you switch the columns around? But you just might feel more comfortable if it was sort of in reduced row echelon form, and doing row swaps might achieve that for you. And the third kind of row operation that you can do is you can do the one where you add on a multiple of one row onto another. Something like that, row 1 minus 2 of row 3. Doesn't really matter what the numbers are. And that row operation does not change the determinant at all. That's why we're so pernickety about keeping the row that you're changing as a plus. So some people, when they do these row operations, they like to do row 1 is replaced with 2 of row 2 minus row 1. But if you do that, then that's a combination of multiplying row 1 by minus 1 and doing one of these, so it will change the determinant. So this will only not change the determinant if the row that you're changing doesn't have a number attached to it. You've got to be really careful about that. So what this means, and it works for columns too, not that you're used to doing column operations, but it does work. I mean, the reason it works for columns too is because the transpose is this determinant of the transpose is the same as the determinant of the original, so you can just switch it around and do it on the other side. Okay, so I am the sort of person that, knowing this in particular, will calculate determinants by doing row operations as much as I possibly can. So let me do an example of that for a second. So I was up to here, right? So I could create a 0 right here by doing row 2 minus row 1. And I know that doesn't change the determinant at all. So I can just go equals this determinant. It's not that these matrices are equal, but the determinants are the same. And now look at all those gorgeous zeros. I can do the determinant here without really hardly any more work. So that would be 1 times the determinant of this. I don't feel like writing determinant. I'm going to do it with the vertical lines, if you don't mind. Minus 0 plus 0 coming down this column. And that would be 1 times 2 times 4 minus 0. 8. Beautiful. That one row operation created zeros that made my calculation easier to do. All right, well, I have one more example of that I want to show you. But before I do, I just want to mention something. So the place in your course where you learned determinants was, a couple of months before you saw eigenvalues. But here we are at the end of the course. We're allowed to connect things together backwards in time now because we've seen them all. So we would like to know that the things that came after determinants, how are they related to determinants? And so there's one more thing that you do know about determinants that's worth doing, is the eigenvalues. Yes, I can. And look, I drew a box on the table and everything to say where my screen is, but I was ignoring it, sorry. So eigenvalues, let's see. I do know that the determinant of any matrix is the product of the eigenvalues. That's useful. Well, I don't know it's useful, but it's interesting. It's useful at least in those situations where for some unknown reason you happen to know the determinant but not all the information about the matrix. So if you know the determinant and enough of the eigenvalues, you can always figure out the last one, because you know that, if it's got the eigenvalues of 1, 3 and 5, but it's supposed to have 4 eigenvalues and you know the determinant, you can figure out the last one. Okay, so it's the product of the eigenvalues, and you find determinants from find eigenvalues from a determinant. Right, you do this lambda I minus A thing, which gives you a new matrix, and you do the determinant of it, and that finds the eigenvalues. And that is why you were taught determinants. No one really cares about determinants, but you were taught them so that you could find eigenvalues, because eigenvalues are way awesome. Okay, so there you go. You were told to do them. And the reason why that works is because if you're going to solve ax equals lambda x and have a non-zero solution, well, determinants being 0... Aha, just a second. I should go back and add that. The determinant being 0 doesn't just mean that A has an inverse. It also means that Ax equals 0 has a non-zero solution. You'll notice something here about the way I study. I'll just start writing down things that I know, and as I go, I will go and fill in information elsewhere. I'm the sort of person, when I study for things, I'll draw got a giant piece of paper and just put everything on it that goes with a specific topic, and any time I think of something, I'll just add it somewhere. And add it in the place that makes most sense for me, because I think spatially. Like my screen on my computer has different places for different kinds of things. You know, I'll put the apps that go with certain things in this corner and the apps that go with other things in this corner, and so I organise my maths information the same way. Yep? Oh, crap. Damn it. Thank you. So if the determinant's not 0, it means it has an inverse? Yes. Whew. Sorry about that. Good noticing. See, aren't you glad I came back to it? So if the determinant's not 0, it means that A does have an inverse. If the determinant is 0, it means that A doesn't have an inverse. And if the determinant is 0, it means that Ax equals 0 has a non-zero solution. And that's why we care so much about this. That determinant being 0 means that lambda I minus A all times x has a non-zero solution, which means you get an eigenvector. Sweet. Okay. So, useful things to think about. If you wanted to prove some things about eigenvalues, it would be useful to know things about determinants. All right, I'm just going to do one more thing. Just a couple of examples of using this information for eigenvalues. But it's just going to be simpler if I go to a new page. Okay. Just to say, I'm just trying to make up a matrix that has eigenvalues that I know. So just give me a moment. I think this may in fact be one of the ones from your assignment. Let's give that a go. Really hope this is going to give me the this is going to give me some things that are lessons that I was hoping for it to give. All right. So let's find the eigenvalues of that the traditional way, not by just guessing eigenvectors, the traditional way by doing a determinant. So lambda I, let's call it A. Lambda I minus A is, let's see, minus A and lambda I. Okay? So we want the determinant of that matrix. All right, here we go. Notice that the first column is a multiple of lambda minus 3. Lambda minus 3 goes into lambda minus 3, it goes into 0 0 times, it goes into 0 0 times, and so I can do this. So that first column, I took the lambda minus 3 out. and left a 1 behind. I'm dividing by lambda minus 3 there, like factorising it out. So that was fun. Excellent. So you'll notice that I can now use that first column to multiply my determinant out without having to worry about most of the rest of the matrix. So it'll be 1 times this determinant minus 0 plus 0. Okay, now that's a 2 by 2 determinant, so I could just expand it out. But watch closely. Okay. If I add this, nope, it's not going to work, just a second. I thought I was going to be so clever. No. So worth a try. Really thought it was going to work. Oh well, I'll just expand it out. But just this allowed me to figure out that there was a lambda minus 3. What a lot of people do is that they'll just figure this all out and they'll get... I really wanted one that was way more spectacular than that. That's okay. Oh well. Yes! Let's do a column operation. Watch this. Column 1 equals column 1 plus column 2. Ready? Lambda minus 3 and lambda minus 3. Now they've both got a lambda minus 3 in them. So I'll take that lambda minus 3 out and be left with this. It's so beautiful. And now, just one more, bear with me. Row 2 is row 2 minus row 1. Lambda minus 7 minus minus 2. And look at that. This matrix now, it's 1 times this minus that, minus 0. And my characteristic polynomial is neatly factorized for me, rather than me having to expand it all out and then factorize it. Anyway, I could probably have done this way quicker, right? But just wanted to make some points about some things. If you happen to notice that it has a lot of repeated values, you can create zeros in places as well that will make it easier to do. So I've seen ones where there's a whole lot of ones. Like if I had like a column of all ones, I would do some row operations to get rid of those ones and make zeros before I moved on to the next step. And I also just think that what's the point of teaching you how row operations change determinants if you're not going to use it for something interesting? So there you go. Was that what you were hoping for when you asked for funky determinant stuff? Good. There you go. Any questions or thoughts about that? Because I'm happy to answer any of them. Yeah? Yeah?
If the determinant is 0, AX has a non-zero solution.
Yep.
If the determinant is not 0, it has one unique solution.
Yep. So let's pull that out. Okay, go back to that. So we're going back to the determinant of A and AX equals 0. So AX equals 0, we know it has at least one solution, x equals 0. Okay, so we know that if we put 0 in that spot, a times 0 is 0. Sweet. The question is, are there any more? So you can imagine doing your row operations and getting a free variable there and ending up with infinitely many solutions. Okay, so we know that that's a solution. So there's at least one. Are there any more? So for example, man. Okay, so for example, that one. So 0, 0, 0 for x, y, z is a perfectly good solution. But so is... Damn it, I did that wrong. Just a second. Let's do that one. So is 1, 1, 1. So we get 4, 0, minus 4, minus 2, plus 1, plus 1, 0, minus 1. So I've got more than one solution. Okay? So, and in fact, I could put 2, 2, 2 and 7, 7, 7 and minus 1, minus 1, minus 1, and they'd all come out to 0. Because it would just be timesing whatever we had by that number. So I've got infinitely many non-zero solutions. So the question is, when are there non-zero solutions to Ax equals 0? And the answer is Ax equals 0 has non-zero solutions if and only if the determinant of A isn't 0. And Ax equals 0 has only the solution x equals 0, so a unique solution, if and only if the determinant of A, wrong way round. It has non-zero solutions if and only if the determinant is 0. Damn it. Which also, A isn't invertible. So sadly, it feels backwards, right? Having non-zero solutions feels like it should go with it not being something, but it doesn't. It goes with it being 0. Yep. So if the determinant is 0, you're guaranteed to be able to get more than one solution. Let's just figure out the determinant. Yes?
I think, I don't know if it was in a lecture somewhere, but I'm not quite sure that you can only get eigenvalues off matrices where the determinant is not invertible, where A is not invertible, is that right?
All square matrices have eigenvalues.
Okay.
But it's, you, just a second. I think I hear what you're saying. I just need to repeat it in a different order, if that's okay. So the idea is that, let's just connect this to eigenvectors. See, this is why I do these things, because we can now learn connections that we didn't have before. So an eigenvector is a non-zero vector with Ax equals lambda x for some lambda. That's what an eigenvector is. So if we rearrange this equation, we get lambda x minus Ax equals 0. So I can subtract Ax from this side and I'll get, might even do that in 2 steps if you don't mind. That. Now I can't, they've both got an x, so I could factorise that out if I wanted, except that I can't leave behind a lambda minus a, because lambda is a number and a is a matrix. So I just need to think about it like this. Now that's a matrix, and so I can do this. Okay, so let's just look back. An eigenvector is a non-zero vector x so that this happens. So I need this to have a non-zero solution. So I need the determinant of lambda I minus a to come out to 0, because that's when you get non-zero solutions. Right. So the thing is that the lambda I minus a, its determinant has to be 0, but the original a, well, its determinant could be anything. Because lambda I minus a, because determinants don't interact particularly well with minus. So lambda I minus a is a matrix of its own, and it has its own determinant, which is 0, and a has its own determinant, which is something completely other than 0. Sometimes it's 0. It's okay for the determinant of a to be 0 as well, but usually it's not. Actually, if you pick the wrong lambda, then the determinant of lambda I minus a won't be 0. You just want to pick the lambdas where it does come out to 0. So with that matrix I had before, which had eigenvalues of 3, 3 and 5, if I had done this lambda I minus a for lambda equals, I don't know, 2, then the determinant would have come out to minus 1 times, would have come out to minus 3. And it wouldn't have come out to 0. And the only way to get it to be an eigenvalue is for that to come out to 0. Yeah. So it's almost as if we've brought, no, it's not almost, it is that we've brought together ideas about determinants and determinants being 0 and solutions to equations together in order to solve the eigenvalue problem. Yeah. And I have never said that bit that I just said there out loud. I've never made the, and I lectured Maths 1A eigenvalues when I did it, so I don't remember actually making that connection as explicitly as I have today, so thank you. Okay. I have no idea what, that doesn't show the actual time, does it? It's not too bad. All right. There we go. I think that's everything I know about determinants. If you talk to David Roberts, he'll tell you all about how determinants are like a derivative for matrices, but I have no idea what he means. So maybe one day I will. Okay, what else was on my list? Oh, so many things. So if you had to pick out of some of those things, if you can read them, subspaces, trig substitutions, integration by parts, dynamical systems, what would you pick? Someone said subspaces, dynamical systems. Yes, it is. Isn't it? You did Markov chains, didn't you? Yeah. What was that growing there? Was that a, damn it, I have to know? All right, well, let me have a quick talk about that. Because while we're on the topic of eigenvalues, why not? So I've talked about dynamical systems multiple times before. You can go and have a look at what I've said before. But this might be a bit different because I make it up as I go along. So the idea of a dynamical system is that you have some sort of situation where there's various variables that describe some numbers. So that's so vague. So you might have like x1 is Damn it, just a second. Let me just think about this. It might be X is the number of, rats, and Y is the number of dogs in some city. And the idea is that you follow it over time and you measure it like all these different times. So you might say that xi is the number of rats at time I, and yi is the number of dogs at time I. Or it might be, for example, that xi is the concentration of sugar at time I, and yi is the concentration of alcohol at time I in some sort of brewing system. Okay, so it can be anything, or it could even be percentages, right? It could be xi is the percentage of people in the city, and yi is the percentage of people in the country. Okay, anything where there's various numbers to describe it, and various numbers, and that they change over time, is a dynamical system. So it may be that you have 3, and maybe this is the number of cats, right? Doesn't matter, they don't have to be 2. And what you hope for is that there's some sort of formula that tells you how to figure out the next one from the one you're up to. So if I was at x10, I'd hope that there's some sort of formula that tells me how to figure out x, y and z for x11, y11 and z11. That's the hope that I have. And so what I want, I hope, is that I have some sort of equation xi plus 1, yi plus 1, zi plus 1 from xi, yi and zi. That's what I hope for. And in the situation in Maths 1A, the only situations that you've been taught how to deal with dynamical systems is if the equations that tell you how to get the next one from the one before can be rewritten in terms of matrices, and that it's possible to do this. Matrix times like that. So I really hope that I can do it with a matrix. Because if I can do it with a matrix, and I can just for my own sanity write this as bold xi plus 1 bold xi, where the bold one represents a vector. If I can do it with a matrix, then as long as I know where I started, if I wanted to know what it was at time I equals 15, then I could just times the matrix on 15 times and it will tell me what happens at time 15. So, e.g., so now I could say that x15 should be start at x0 times by a, and that will get me to x1, times by a, that will get me to x2, times by a, that will get me to x3, and there'll be 15 of them. Sweet. So now I can turn a problem about what will happen to my system after a long time into what happens to my matrix when I raise it to a high power. That's the idea. So this may be a situation in which you might want to know the high power of a matrix, only you don't actually care that much as you thought you cared about the high power of the matrix A, because we can use eigenvectors to give us something really useful here. Yep?
When we're solving the diagonalization,
Mm-hmm.
in the past assignments, we have to do all this work, and it turns out that you can just place the eigenvalues on the diagonal.
Yep.
Do you have to go through all the stacks of work of proving D equals P inverse AB?
So just for the those who couldn't hear that, when you do diagonal, oh crap. when you do diagonalization, which is not directly related to this right now, but when you do diagonalization, you get this P inverse AP comes out to a diagonal matrix with the eigenvalues on the diagonal. Do you have to go to all the effort of going actually doing the multiplication of P inverse times A and then times P? No, you don't, unless you're specifically asked to. So the whole purpose of learning that is so you don't have to do that. As long as you're sure that your eigenvalues are really eigenvalues and you're sure that your eigenvectors are really eigenvectors, then you can just write it down. You don't pretty much you don't even need to calculate what P inverse even is. You just say if P is this, then P inverse AP will come out to this without doing the actual calculation. You just have to find the eigenvalues. That's the question you're asking? Good. Okay, so here's the thing. If x naught happened to be an eigenvector for A, then AX naught would be lambda x naught for some lambda. And then I'm going to do an exclamation mark in the middle of my sentence, it's bad grammar. Then, well, let's see, x1 would be A times x naught, which would be lambda x naught. And x2 would be A times x1, but x1 was lambda x naught, which would be lambda lots of ax naught. But ax naught was lambda, and so I get lambda squared. Interesting. So every time I multiply by A, I just multiply by lambda this time because it's an eigenvector. So x to the x15, etc., would be lambda to the 15 times x naught. So if I was lucky enough to pick an eigenvector as my original x naught, then I wouldn't even have to do matrix multiplication. I just have to keep multiplying by the number lambda instead of the matrix A. Now that would be extremely convenient if your original vector was an eigenvector, but that's the idea behind this. And here's the really, really clever part. Most matrices, your eigenvectors can make a basis. So you can construct any vector you want out of eigenvectors. For most matrices, you can make a basis of eigenvectors. So no matter what x naught was, you could write it as A times eigenvector 1 up to however many you need times eigenvector n. And A times each of those is just timesing by the matching eigenvector value. And A times x naught would be A times A1 V1 plus A times AN Vn. And that's an eigenvector, so you just end up with lambda. Each V would have its own eigenvector value. So that means that if I can find a basis of eigenvectors, I never have to do matrix multiplication again. All I have to do is multiply by the correct numbers. Now that's convenient. That's why eigenvalues can be so useful, because once I've found them, I've done all the matrix multiplication I ever need to do. All I need to do is do this. Okay. And even better, best with a proper example rather than random things. I'm going to put some decimals into here instead of whole numbers, because that's going to give me what I would like to have, but I just need to think carefully about what my eigenvalues are going to be, so bear with me for a second. Okay. I'm going to run with that. So that's going to be my dynamical system. So I'm going to find the eigenvalues. Let's call this A. Lambda I minus A is 0.8 minus 0.3 minus 4 with some lambdas. Okay. Man. Just going to check what happens if I add these together. Minus 0.7. Okay. Column 1 is column 1 plus column 2. Minus 0.7. I can bring my lambda minus 0.7 out. Now, it was just a lucky guess. Well, I mean, I set this up so that that would happen, but that would be just a lucky guess of attempting to see what would happen if I added my columns together to see if it gave me something that matched in both positions. So I get lambda minus 0.7. So this one I'm going that minus that. What's that? Yep, okay. Sweet. I think I've done that, right? Minus 0.4 plus 0.8 would be 0.4, yep. And if I add those two things together, I get minus 0.3, which is totally the trace. Excellent, everything works. I'm just checking to see if I've got my answers right. It's not a full check, but I do know that if I add the eigenvalues together, it should add up to the same as the trace. Okay, so here's the thing. I'm not even going to figure out what the eigenvectors are. I know that because I've got two different eigenvalues, then the two eigenvectors that go with them are going to be independent of each other. So the matching eigenvectors are linearly independent, and so therefore I can make a basis of eigenvectors. So I'm going to have lambda equals 0.7 goes with V1, and lambda equals minus 0.4 goes with V2. Oh, yes. All right. So that means that no matter what starting position I have, that x naught will be something times V1 plus something times V2. Because it's a basis, no matter what x naught is. And so, let's just make sure we've got this right. x1 will be the matching eigenvalue times this eigenvector, and the matching eigenvalue times this eigenvector. And x2 will get that squared. And if we just keep doing that over and over, the nth one where'd my B go? Now let's look at this very closely. 0.7 is a number that's less than 1. If I do a very high power of a number that's less than 1, I'm going to get a very, very small number. 0.7 squared will be 0.49. 0.49 squared will be close to 0.25. 0.25 squared will be close to 0.125. It's just going to get smaller and smaller the bigger that n gets. So as n gets bigger, 0.7 to the n goes to 0, and minus 0.4 to the n also goes to 0. They're both less than, like closer to 0, closer to than 1 to 0. And so therefore x to the n will go to 0 v1 plus 0 v2, which is 0. So just to summarise, no matter what x naught is, xn goes to 0 as n gets bigger. So without knowing anything other than the eigenvalues, I was able to figure out that this dynamical system, no matter what I start with, will always just tend towards 0 because the eigenvalues are both less than 1. That's why eigenvalues are so useful. Now, let's do some what-ifs. It's always good when you do these types of problems to not just finish it and go, cool, I could do that problem. Think, what would happen if it was a different? What if my eigenvalues had come out to this? What if there'd be 1.1 and 0.2? Well, then my x naught, my xn would have been 1.1 to the n times a v1 plus 0.2 to the n times b v2. And this one would go to 0, but this one wouldn't. So 0.2 to the n would go to 0, but 1.1 to the n is just going to get bigger. It just increases. So in that case, whatever numbers that this x and y represent, they'll just keep getting bigger and bigger. Okay? If they represent percentages, then you can always convert them back to percentages after. So what if the xi and the yi are percentages? Well, in that case, numbers less than 1. In that case, suppose you got v1 was like, I don't know, 2, 3, just for argument's sake. Then what you get is that xn it's not a fraction, David, it's a vector. Now I don't care what this bit is because that's going to go to 0 anyway. So it's going to be approximately equal to this. If n is really large, that says large n. If n is really big, this will be nearly 0, and you'll just get this bit. This will be huge, but it'll still be there. But look at this, they've both got a 1.1 to the n. So if I want to do them as percentages, so I've got, so the x, just a second, xn and yn would be 1.1 to the n times a times 2, and 1.1 to the n times a times 3. If I want them to be percentages, I sort of want to do them out of the total. Times a times 5, that's the total. And as percentages, this would be this divided by this as a percent. Which is 2/5, which is 0.4, which is 40%. And yn as a percent will be 1.1 to the n a times 3, which is 0.6, which is 60%. So all the n's cancel out. So it turns out that as n goes to infinity, as for very large n, the y's are 40% of the total, and the x's are 40% of the total, and the y's are 60% of the total. So if this was populations living in the city versus the country, you'd know that while the populations to continue to grow, you end up with 40% in the city and 60% in the country, no matter how big they get. That's the sort of idea. So I do these what-ifs so that when I'm studying myself, so that I can try and figure out, what if they just gave me some extra information? Could I do more? So you could imagine now an exam question where they just tell you one of the eigenvectors and don't tell you the other one, because you don't need to know, because it goes to 0 anyway, when n goes to infinity, depending on the sort of information they're asking. One of my problems with Maths 1 and all first-year courses in all disciplines, maths or otherwise, is a whole lot of stuff in it, with all those little nuances that can come up if you ask a what-if question. That's why it's so good for you to, when you're studying, ask yourself what-if questions. And if you can't answer the what-if question, that's the whole reason to have something like a Maths Learning Centre, so you could come and ask, hey, I did this question, what if this was a negative number? And I could say things like, yeah, they won't give that to you because it's too hard. Or, yeah, I reckon you can do that and sit there and help you figure it out. If you spend time doing what-ifs, then you'll do questions that you've never seen before, which is what your exam questions are going to be like. I mean, some of them will be similar, but there's always going to be at least a few of them that are sort of things you've never tried. So practicing doing things you've never tried is a good thing. Not least of, funny story, not funny. It's not funny at all, but anyway, interesting. The other day I was helping one of the second years, and we went, and he did a what-if question, and I said, this would totally be an awesome assignment question. So I emailed the lecturer and said, this would be a good assignment question. He said, yes, it would. Maybe I'll use it next year. And there was a first-year student there with me at the time when I had this conversation. So now he knows one of next year's assignment questions because we did a what-if. There you go. It's not going to happen very often, but it could. It could happen to you. Okay, I've got about, half an hour? If I'm paying attention. Oh, 40 minutes, even better. What am I going to do next? Unless people have other what-if questions to go with the dynamical systems, which I'm happy with. I have no idea what's on your exam. In a literal sense, I'm not pretending, I really don't. I'm not involved in the management of Maths 1. I belong to the whole university, so I don't teach any of the courses, except some of the med courses. They pay us extra to get us to do that. But I'm not involved in running your course, so I have no idea what's in your exam. It's not impossible. If you look at the last 5 years, however many years you've got, if it's occurred at least once, then it's not impossible for it to happen again. And plus it's a use of eigenvalues, so you're going to have to do dynamical systems, you have to find some eigenvalues or use information about eigenvalues, so it's not the worst thing for them to ask because it does two things at once. So, yeah. What's the plan next? Were you the person who emailed me? No?
Yeah, I emailed you.
Anyone else have preferences for what things they might like to talk me to talk about in the next 40 minutes? Sorry? Bases? Okay. All right. Can I ask you what you wanted to know about logs?
Just to practice again. I watched your video, it's brilliant.
Okay.
Yeah.
Or maybe you see, I've done so many basis ones, but it's every semester. Like, it's just one of the things you have to talk about a lot to get. So maybe see, they're all, this is my problem with doing these request sessions. Of course, I could just declare another one for tomorrow and keep going then, right? If you're interested. Maybe I will. I've booked the room, so, and no one else has asked me for anything, or at least people who've asked me for anything, their exams are later, so I'll do a Maths for IT one next week or something. So, okay. I might go basis first, if that's okay, because that might set you up for doing more of your study overnight. Okay. Well, what sorts of questions do people have about basis? Might write them down so that I can keep track of them. What questions have we got? What sorts of things are a bit hazy, or you think you understand but you're not sure, or you have no idea about, or when you're faced with that sort of question in a past exam, you're really not sure what to do, or how to tell if you're right? Any of those things. Or just random thing you think is really cool, whatever. Okay, anything else? These are our questions that people are asking. That's what we want to know. That's a pretty good thing to know. I'm not saying it's bad, it's just, okay. All right, cool. Yep. Yeah.
So you can have a basis of 0, 1, or 0 and 50.
Are there like better ones? Okay, cool. Well, I might run with that. If you come up with anything along the way, just ask. All right. So it's really important when any time you want to know how to do something to hold in your mind the concepts that are involved. Because without knowing the concepts, you can't guide yourself of what to do when you forget. So if you forget what to do in a procedure, if you know how the concepts fit together, you might have a chance of figuring it out. But if you don't know, if all you know is the procedure and you don't know what the idea is, then if you don't know how to do the procedure, you're stuck, you can't do anything. So that's why I'm just going to have a quick idea of what a basis is. I will not talk at length about what a subspace is, because that's a whole other discussion. But anyway, so a basis is a piece of information about a subspace. Now, that doesn't tell you what it is, but that's what it's for. I find that a useful way of categorizing information. There are some things which are objects in their own right, like numbers or matrices or subspaces, and there are some things that don't exist without the other thing. So the determinant of a matrix doesn't exist unless the matrix is there. It's just a number otherwise. So the determinant belongs to a matrix. It's information about the matrix. Subspace is a thing, and a basis just belongs to the subspace. It doesn't exist all by itself. Okay? So there's no point saying this is a basis without saying what it belongs to. And the information about a subspace that it is it tells you how to construct the entire subspace out of linear combinations. That's not the formal way of saying it, but it says how to construct the whole subspace out of linear combinations. That's what it's for. Now, that's not quite enough to make it a basis, but that's the general idea. Okay? So, therefore, the way to find a basis is to construct your whole subspace out of linear combinations. Once you have done that, then you have a basis. That's the thing that I hold in my heart to guide me when I'm journeying along the road to a basis. Okay? It's all very... I don't know if any of you have ever seen the Thumbelina animated film, but yes, you don't need a map to guide you. Just follow your heart. So this is what I have in my heart for finding bases. Okay, so that's the idea. Now there's some technical details, but we can get to them now. So your technical details are this. I'm going to do them in the not the order they're presented. Okay, so the technical details is that a basis... No, this is the order they're presented, don't worry. A basis for a subspace, what do they call them? W traditionally, is a set of vectors that has two rules. Rule number one, they have to span the subspace. Just thinking of the grammar of this sentence. It's a set of vectors, so therefore it has to, a set spans. Yep, okay. And two is linearly independent. This one is the most important one. The linearly independent is still important, but less important than the spanning. And the reason is that the span is this. It's making things out of linear combinations. That's what span is. So that is everything in W is a linear combination of the vectors. Okay. So now we have a specialized terminology for it now. It's span. The purpose of a subspace is to reconstruct your subspace as a span. Okay. So that means to find a basis, I have to rewrite my subspace as a span. That's the first thing I have to do. I'm going to write that down in a second, but the other thing is that this linearly independent bit is a guarantee that your list of vectors is as small as it can possibly be. Okay, I don't want any extra ones that mean that I don't need them anyway. So it's not just out of linear combinations, it's out of linear combinations in the most efficient way. Efficiently. So the linear independent guarantees that I haven't got any extra ones that I don't really need to be there. That guarantees I have the shortest list. There will be many, many shortest lists, and some of them, as you say, may be better than others, but we'll get to that in a second. Okay, so the first thing you need to do to find a basis is rewrite your subspace as a span. And two, make sure they're linearly independent. There are other ways to find a basis, but they are still based on imagining that it is a span, even if you don't write it as a span. Okay? Okay, examples. So there are there are two main ways of telling you what a subspace is. One is to tell you a list of equations that have to be satisfied to be in the subspace. And two is to write it as a span to begin with. All other ways are usually one of those two if you think about it. So here we go. Let W be this. It's the set of vectors with coordinates x, y, z, t, such that x minus 3y is t and z plus 5x is 0. Okay. So let's just think about what this object is and we'll find a basis for it, right? So my first I'm going to answer this. In Maths 1A, no one really cares if you've got the inverted commas best basis. Whichever basis you like, and no one really cares. The solutions will have a fairly efficient way of finding a basis which will give a certain answer, but the people marking your exam will accept anything as long as it really is a basis. Okay, so that's the answer for Maths 1A. In Maths 1B, you learn about better bases than others, but it's not part of Maths 1A. Yes. Okay, so we want to find a basis. So if we want to find a basis, we have to rewrite W as a span. At the moment, the way of telling us what W is merely tells us how to check if something is in W. If I had a random vector like 1, 1, 1, 1, I could tell if it was in W by seeing if it satisfied the equation. So let's see, 1 minus 3 times 1 is not 1. And so no, 1, 1, 1, 1 is not in this subspace. But I could check as many vectors as I want, and I may never find something that's actually in the subspace. I am guaranteed that 0, well, let's just see, 0, 0, 0, 0, yeah, that works. I can sub-zero those coordinates into both of those equations, and it works. So, good. If 0 wasn't in there, then it wouldn't be a subspace, so I'd be stuffed. That'd be fun in an exam. They do it wrong, and you say, 0 isn't in this, it's not a subspace, it doesn't have a basis, and just stop. That'd be... I would be so happy if someone came to me and said that. I mean, the exam writers would be so upset with themselves for putting a typo in that meant it wasn't a subspace. But I'd be happy that all of you came out and said, David, you told me what to do and I did it. Right, all I have at the moment is a way of telling if something's in the subspace, but I don't have a list of what all the vectors are. And that's the idea. I need to write it as a span, but I mean, really, that's just secondary to writing it as a way of telling what all the vectors are. I can't know if it's a span unless I find all the vectors that are in it. So I need to do that. I need to find all the vectors that are in W. Because once I've found all the vectors in W, then I'll be able to tell if it's a span or not. I mean, I know it's a span, it's a subspace. All subspaces are spans of something. And to find all the vectors in W, that means I need to find all the vectors that satisfy both of those equations. All right? So let's do it. I mean, that's two linear equations. We know how to deal with that. That one would be x minus 3y minus t equals 0. So let's see. We have x, y, z, and t. And we have 1x minus 3y's, no z's, and a minus 1t equals 0. We have no 5x's. No y's, 1z, no t's equals 0. I know how to do that. Row operations, free variables, la-di-da. So let's see. Now, I could, if I wanted to, find the reduced row echelon form of this matrix if I desired, and that would tell me where the pivots were and the free variables were. And that's normally what you'd do. However, it seems to me that it would be much more efficient to not put my pivots in the traditional places. So when we did linear optimization in Maths 1A, you spent all this time being convinced that you could put the pivots wherever you wanted. So you pay, I want them in column 1 and column 3, and then I make all the other ones 0, blah, blah, blah. So since you are now convinced that you don't need the pivots to be in the first couple of columns for, like it is for reduced row echelon form, you just need to be convinced that you need to fit an identity matrix in here. The biggest identity matrix you can, as much as you can fit. And I notice that this is the second column of the identity, and this is the first column of the identity, and so I can put an identity matrix column there like I did when I did linear optimization. So I'm just going to do one row operation, which is row 1 is minus row 1. And I'm going to make the variables that goes with those ones my pivots, because a pivot belongs to an identity matrix column, and they're my two columns of an identity. No. Not if you don't want to. Now, if that makes you feel uncomfortable, as it might, just do your traditional reduced row echelon form. But I can guarantee that your lecturers would have written this question and calculated how long it took under the assumption that you didn't have to do very many row operations. So, just for future reference. However, it would only take, what, 3 row operations for me to get this into reduced row echelon form, and I will do that as well, just to show you that it's okay, all right? But first I'm going to do this method. Okay, so I'm going to put my pivots here, and these ones are free because they don't have an identity matrix column to go with them. And so therefore I'm going to go let x be, I've already used t, haven't I? X be s and y be r. And then according to this equation, I've got minus x, which is minus s, plus 3y, which is r, plus 0z, plus t equals 0. So the t is equal to s minus 3r. And according to this equation, I've got 5s plus z equals 0, so z is equal to minus 5s. Now, what's the whole point of this? Remember that the goal of the, don't lose sight of the goal. The goal is to find what all the vectors are. So the vectors had 4 coordinates, right? And the x is s, the y is r, the z is minus 5s, and the t is s minus 3r. So I have now found all of the vectors in this subspace. If x, y, z, t is in W, then it can be written this way. And in fact, let's see. There's a 1s here, no s's here, minus 5s's here, and 1s here. There's no r's here, 1r here, no r's here, and minus 3r's here. I can rewrite this like that. If I multiplied this by s and this by r and added them together, it would produce the same answer. And look at that. It's a linear combination. I have rewritten W, all the vectors in W, as linear combinations. So in fact, W is the span of 1, 0, minus 5, 1, and 0, 1, 0, minus 3. Okay, so I've rewritten it as a span. Now I just need to make sure they're linearly independent. And yes, they are, because of the positions of the zeros. This one can't be written as a combination of that one because of the 0 in this position means I can't ever make a 1. So these are linearly independent, and so therefore 1, 0, minus 5, 1, and 0, 1, 0, minus 3 is a basis for W. Just be careful with your language there. With the span, it's W itself. Without the span, it's a basis. Because technically, this is just those two vectors. With the span, it's the entire of W. Now let me just track back a bit and show you that it is actually okay to do your traditional reducer echelon form. Now, I could have done this, or back here, I could have done row 2 is row 2 minus 5 of row 1, which is the traditional first step of doing my reduced row echelon form to make a 1, 0. So this minus 5 of that, 0 minus 5 times minus 3 would be 0 plus 5 times 0 plus 15. This minus 5 of that is 1, like that. And then I could do row 2 is a 15th of row 2. Zero, 1 15th. 5 15ths would be a third. And then I could do row 1 is row 1 plus 3 of row 2 to get the 0 here. So 0. Like that. Minus 1 plus 3 times a third would be minus 1 plus 1, which was 0. Okay. And so in this case, I could have, these would be my pivots. And these would be free. And so I would go, let Z equals S and T equals R. And then I'd have X plus a fifth of S is 0, so X is equal to, and Y plus a 15th of S plus a third of R is 0. And so I would have gotten this. I actually feel much more comfortable writing vectors as columns, because in Maths 1A, unless otherwise stated, a vector is almost always a column, and there's more room to fit things. So X is minus a fifth of S, Y is minus a 15th of S minus a third of R, Z is S, T is R, and I get S times minus a fifth, minus a 15th, 1, 0. And T is, no, not T, damn it. I'm so used to using T. Right. And so this would be my basis, these two. I should finish that off. This looks very different from the other basis I found, but that's okay. There's all these different choices for what the basis could have been, because there's infinitely many vectors to choose from, so there's infinitely many bases that I could have gotten. This basis is harder to read because there's all these fractions in it. I mean, fractions are not worse than whole numbers, they're just harder to read. And so that's why I chose to do it the way I did, because then I got nice, pleasant whole numbers. Yeah, it looks totally different to that one. Though look at these two. This one is like minus a third of that one. And this one, well, that's much harder, but essentially I should be able to make these two out of those two, and I should be able to make these two out of those two, because that's how bases work. Any one basis can be constructed from any other basis for the same subspace. So, however, whichever of these you did in your exam would be accepted as correct, because they're both correct. But I like putting together bits of the course, right? Oh, I've been told I can put pivots wherever I want. Excellent, that avoids fractions. So, all right, let's do some what ifs. Anyone got some for me with finding a basis? What if there was only one equation? What would you do if there was only one equation? Okay, well, I could do the same thing I did with the other thing, right? I could say, all right, well, I'm going to need to find all the vectors, which means I'm going to need to solve this equation. I could do what I did last time and rewrite it as a linear equation and just make a matrix with one row. One row. So I'll need to do some row operations in order to get my identity matrix, but the one by one identity is just the number one, so there's a pivot just here already, which makes this a pivot and these are free. Crap. Makes this a pivot and these are free. And so I'll give those free variables letters. I could just keep them as the letters they are, but it's tradition to change them. So I could say let y be equal to s, z be equal to r, t be equal to q. Just do my alphabet backwards. And so I've got that x minus 3y, but y is s, plus 0r, minus 1t, but t is q, equals 0. And so x, y, z, t is, the x is 3s plus q, the y is s, and the t, z is r, and the t is q. So s lots of 1, 3, 1, 0, 0, plus r lots of 0, 0, 1, 0, plus q lots of 1, 0, 0, 1, and there's my basis there. So that's one way of doing it. Just because you've only got one row doesn't mean you can't make a matrix with one row. There is another way. Okay, so I don't know if it's occurred to anyone else, but didn't that seem like a bit of a waste of time to say s and r and q? Couldn't I have just left them as y and z and t? And then I would have just got y times 310 and z times 0010 and t times 1001. And it would have been perfectly acceptable. It's still linear combination. Okay, so knowing that, or, so we know that x minus 3y is equal to t. Yep. So if x, y, z, w is in, sorry, not w, if x, y, z, t is in the vector, the subspace w, then t is equal to x minus 3y. I'm just going to sub that in. T is x minus 3y. And that's x lots of 1, 0, 0, 1, and y lots of 0, 1, 0, 0, sorry, 0, 1, 0 minus 3, and z lots of 0, 0. Ta-da! So therefore W is the span of these things. And they are a basis. Magic. Okay, so just be aware of that. If you've only got one equation, there's actually a pretty fast way of doing it. In fact, I could have done that even with my two equations. When I had my two equations back here, my t can be written in terms of x and y, and my z can be written in terms of x. And so I can just say x, y, minus 5x, x minus 3y, and separate that out. So if your equations are simple enough, you can rewrite all of the variables in terms of just a couple of them. And it automatically writes it as a span, which is very, very cool. The only thing that's going to be harder is that you may, in that process, not end up with linearly independent vectors, and you're going to have to check. If you do it by row operations, you're guaranteed that the vectors you get at the end are going to be independent. So. And that does give me something else that's worth thinking about. What if your vectors aren't, your subspace isn't written in terms of equations? What if it's already a span? How would I find a basis then? I mean, it's already written as a span, so I would expect this to be a basis. Only I have to do the bit where I check it's linearly independent, because I don't know how these were made. If they were made from doing my row operations, I'd know they were independent because of the way they were made, but I don't know, so I'm going to have to check. If any one of them is a linear combination of the others, I should be able to just... oh crap, sorry, just a second. Right. If any one of them is a linear combination of the others, then I know they're not linearly independent, and I can remove one of them. So I could stare at them until I notice whether they're linear combinations of each other. I don't know. If this was going to be a combination of those two, it would have to be 2 of this one, because of that 0 there, right? The only way I'm going to get a 4 in this position is if I go 2 of this second one. And 2 of that second one is minus 2, 4, 1. Ooh, interesting. And if I want to make a 4, I could do a 3, right? Yes! Magic! It's almost as if I set it up that way. So I know they're not linearly independent because one of them is a combination of the others. Now that's not the only way to tell if they're linearly independent, but you know, if you notice it, it's a good one. And so in fact, W is just the span of these two. Because I can make that third one out of the first two anyway. So anything that I could make as combinations of these three, I could just as easily make a combination of these two, because that one's already a combination of those two. And so now they are independent, and so I've found a basis. Yay! Okay, that's one way. So did you see, I hope you noticed some of my reasoning. If this is going to be a combination of those two, that 0 tells me what multiple of this it has to be. And then I can guess how many of the other one I have to add on. That's a sort of a useful way of trying to do it in your head. On the other hand, what if you didn't notice? You just stared at them and didn't come up with anything, and you just had no idea whether they were independent or not. How would you tell? I really want you to answer me, somebody. Chuck them in a matrix, yeah. As columns. Be really careful if they're listed as rows, you have to put them in as columns. If they're listed as columns, obviously, but if they're listed as row vectors, you have to put them into the matrix as column vectors in order for this procedure to work. You know, or this is one of the ways you were taught to tell if vectors were linearly independent. Technically, there's a 0, 0, 0 here. Not that you really care, but that's technically there is a 0, 0, 0 there. Because what you're attempting to do is find a linear combination of the 3 that produces the 0 vector. Because that's the definition of dependent and independent, of being able to produce the 0 vector. Like A1, V1 plus blah, blah, blah. But you don't have to include the 0 because it's not going to change when you do the row operations anyway. So, row 3 is row 3 minus 3 of row 1. Oh man, 3.5. Oh, that's cool. Huh. Technically, you're not supposed to divide by 2, you're supposed to times by 1/2, but no one really cares. So I could divide that one by 2. It might be, since these both have got a 7 in them, I might divide them by 7, and it might be a little easier for me to see what's going on. And here's me writing the zeros every time like a nung, even though I told you you didn't have to. Interesting. And row 2, that's row 3. They're going to cancel out, aren't they? All right. Sorry. So I can tell now that they're not linearly independent. Because if they were, I would be able to produce a pivot in every column, and I can't produce a pivot in this column anymore because of this row of zeros. Now, a row of zeros doesn't always tell you that they're linearly dependent. If it's a really long matrix, you can have lots of rows of zeros before it stops there being a pivot. So it's all about where the pivots are, and rows of zeros are only important in so much as they stop there being pivots. So can't put a pivot here. So that means they're linearly dependent. Okay, but because they're linearly dependent, there can't be a basis, which means that one of them must be a linear combination of the other two. And the way one of them must be a combination of the other two, and this in fact tells me it's the last one that's a combination of the first two. Because if I finish this off, it would tell me what combination of these comes out to 0, and I'd be able to rearrange it. And also, look what happens if I only include the first two. I get a pivot in both columns, which means they're independent. That's the idea behind it. So if you end up with your pivots separated by free variables, you've got to remove all the free variables. But be very, very careful. It's not these that are my basis. This just tells me information about my basis. So it's actually, this tells me, therefore a basis is these two. like that, because they're independent. You see, you can tell, you do a lovely statistics investigation of the length of time David's been lecturing for and how often he has to be asked to pull it up. I'm good at remembering at the beginning, but as I get tireder, I forget.
So what if you had the identity like in the middle of the matrix? Would you just say, like, for example, the first column didn't have any pivot in it? But you just concluded that has to be that column matrix has to be thrown out?
You might have to draw one. You could draw. I could bring it back from you. You don't have to come.
No.
No. So you're saying that what if the pivots weren't over on this side but were elsewhere? It doesn't really matter where they are. Even if the first several of them are free, they're not the ones you want. You want the last ones. And if you did your row operations not in the traditional order, such that your pivots ended up in different spots, then the ones that went with pivots would be the basis that you're looking for. Because remember, there's multiple different bases. So one thing I want to do is to get you to compare something, just to make sure that you've noticed that they're different. Good, I can just fit enough of them to remember what they are. So in this one over here, I did row operations on a matrix, and it told me a basis. And this one, I did row operations on a matrix, and it told us a basis. That's how they're the same. How are they different?
The second one, you're just checking if they're linearly independent.
Mm-hmm.
The first one is you're finding the span.
Cool. So one thing you've said, this one I'm checking if they're independent. This one I'm finding the span. So the major difference is that I'm looking for a different result. But what that has meant, I'm not going to just ask you, because if I was in a classroom, I would get you to find even more differences. In this one, my basis came from the free variables. I added my R and my S, and I used those to create my vectors from the free variables. In this one, the basis came from the pivots. They're completely opposite to each other. And in this one, the basis was actually listed in the original matrix. In this one, the basis doesn't live in the matrix at all. You had to create it yourself out of the free variables. And the reason for that is what we figured out just then, is that I have different purposes. This one I'm trying to go from equations, and my matrix represents the equations, and I need to create vectors. This one, my matrix represents vectors, and I need to find vectors within that list. So that's why they're different. It's very easy to think back on it and go, oh, I'll just do row operations, and then maybe do free variables in this one, and original matrix vectors in this one, but you've got different purposes. So that's why I hold on to that thing in my heart which says I need to rewrite it as a span. If it's already a span, I don't need to find a span. I just need to find the vectors. If it's not already a span, I need to find the vectors, which is what the free variables are for. There we go. That's enough for now.